Introduction: from awareness to action. In the previous episodes, we answered two critical questions. Why HVDC systems are becoming cybersecurity targets, and where cyber risks actually exist inside converter stations. Now comes the most important question of all. How do we actually secure HVDC systems in practice? Cybersecurity for HVDC is not a single firewall. It is not one software patch. And it is not a checkbox in a project document. Cybersecurity for HVDC is a layered engineering strategy, combining international standards, secure communication protocols, proper network architecture, and resilient control and protection design. This episode focuses on real deployable solutions. IEC 61852 in HVDC systems. Why IEC 61850 matters. IEC 61850 is the backbone of modern digital substations and HVDC converter stations. It enables interoperability between IEDs, high-speed communication using goose and sample values, and logical nodes for control, protection, and monitoring. In HVDC systems, IEC 61852 is widely used for converter control coordination, DC protection signaling, and station-level and system-level automation. Without IEC 61850, modern multi-terminal HVDC systems would simply not scale. The cybersecurity gap in IEC 61850. However, there is an important reality we must acknowledge. IEC 61850 was not originally designed with cybersecurity as a priority. Key challenges include goose and sample values were originally unencrypted, communication is based on a trust model, and no native protection against spoofing or replay attacks. In an unsecured environment, an attacker could inject false messages that look completely legitimate. This exact gap led to the development of IEC 62351, IEC 62351, Securing Power System Communication. What is IEC 62351? IEC 62351 is a cybersecurity standard specifically created to protect IEC 61850, SCADA protocols, and power system communication networks. Its main goal is clear: add security without breaking real-time performance. Key IEC 62351 security features include authentication, which ensures only trusted devices communicate and prevents unauthorized IDs from injecting commands. Encryption, which protects data confidentiality and prevents eavesdropping on control and protection signals. Integrity protection, which detects message tampering and prevents false data injection attacks. And secure goose and sampled values, which use digital signatures for critical signals and time-aware validation to block replay attacks. For HVDC systems, IEC 62351 is not optional. It is essential. Network zoning and segmentation. The end of flat networks. Traditional power systems often use flat network architectures. In modern HVDC systems, this is extremely dangerous. A secure HVDC system must be built using network zoning. Secure zoning in HVDC stations includes the process zone, sensors, merging units, actuators. Bay, control zone, converter control IEDs, protection relays, local HMIs. Station zone, SCADA servers, engineering workstations, data historians, and enterprise external zone, remote access vendor support monitoring centers. Each zone must be protected using firewalls, access control lists, and intrusion detection systems. No implicit trust between zones. Every communication path must be explicitly permitted. Redundancy and fail-safe design. Cybersecurity is not only about prevention. In HVDC engineering, we must assume one thing: a cyber attack will eventually happen. So the real question becomes, what happens when something goes wrong? Redundancy strategies in HVDC include control, redundancy, dual or triple redundant controllers, independent communication paths. Protection independence. Protection functions isolated from control networks, hardware-based fallback logic, and fail-safe converter behavior, default safe blocking modes, conservative operating limits under uncertainty. The cyber resilient design principle states that if communication is delayed, corrupted, or completely lost, The HVDC system must still maintain DC voltage stability, avoid uncontrolled power oscillations, and prevent cascading failures in connected AC grids. This is the difference between secure systems and resilient systems. Best practices for HVDC cybersecurity. Beyond standards and architecture, successful HVDC cybersecurity relies on discipline. Key best practices include security by design, not add-on, continuous monitoring and event logging, regular security audits and penetration testing, strict access management and authentication, and training operators for cyber-physical incidents. Cybersecurity is not only a technical problem, it is also a human and organizational challenge. Conclusion: securing the backbone of the future. Securing HVDC systems requires more than compliance checklists. It demands IEC 61852 awareness, IEC 62351 enforcement, network zoning discipline, and a fail-safe engineering mindset. HVDC is a pillar of the future power system, but without cybersecurity, it can become a single point of failure. Designing secure HVDC systems today means protecting the stability of tomorrow's energy networks. Thanks for watching. Stay curious.